Good afternoon, everybody. My name is Francesco Cavaliere. I'm going to present a work I'm doing lately on a framework that aims to help the development of vehicle routing heuristics. First of all, some special thanks to Luca Corsi and Thibaut Vidal for all the helpful discussion we had, and also for the insight they gave me about the respective algorithm. So let's start with a disclaimer. This is very early work. It's not ready. It's not really close to be ready. But still, I kind of dedicated quite a good amount of time to it. It first started as a personal project in my free time. Then now lately, it's kind of becoming a more research project. So I kind of accumulated quite a good amount of tools and lessons for myself that I hope that could be helpful for anybody. So when we look to the vehicle routing literature, one aspect that we might find is quite evident that is the amount, all the variety of many different VRP variants that has been proposed during the years. And from the more famous one to the hybrid one and all the kind of variation arising from real world scenario. And it's not always easy to navigate throughout all this variety. On the other side, if we consider the algorithmic aspect, we also find a kind of a similar scenario where many different techniques were also proposed. And also in this case, it's not really easy to understand if a technique that works very well with a variant is also kind of extensible to other types of variant. So from a framework point of view, what really I would like to achieve is a way to, on one side, being able to develop algorithms and study techniques for multiple variants without having to always deal with all the details, but just starting from the ground up and treat with a class of variants all at once. And on the other side, I would like to make easier this process of building new algorithms. So starting from how in the literature, how the approaches that try to deal with more than one variant, well, we kind of find three rough subgroups. One is represented by the easy algorithms, easy in a positive way, like Caesar in this case, selection induction by string removal, which make the simplicity of the technique one of the main characteristics. And being a simple technique usually these algorithms are also easier to extend since they have less components that need to be customized. However, still, like from a framework point of view, simplicity cannot be really a constraint. Simplicity can be a good goal that one can try to achieve with his algorithms, but cannot really be like, okay, you can use this framework, but your algorithm must be simple, otherwise nothing will work. Another group of techniques that we can find is what are called also rich solver, which in practice consider very big variants with a lot of different characteristics that kind of are a union of all the constraints we would like to consider. However, this kind of approach introduces inefficiencies when we are considering subvariants, like we are considering a very generic VRP variant, and then maybe we are only testing on CVRP, but still we are paying for all the other constraints that we are handling without using it. Then the third class of heuristics that we may find are the one of the framework. We have different examples of this. One that has been cited many times today is the UHGS of Thibaut. We have also the LKH3 of Kellersgaon. These frameworks are kind of a way that pretty much make available to the user some kind of components that can be personalized and can be used to model each different variant. And then the framework considers this component to customize the algorithm itself. So in a way, they are able to adapt the framework is able to adapt to each specific variant. Considering the work of the UHGS, they consider, and I also consider the same division in the framework, to describe a WRP variant, they consider three different type of attributes. We have sequence attributes or shape-related attributes that usually are related to the shape of the root, the priorities that we might have. Beckholz, Leinol are a classical example. Then we have assignment attributes that usually have to deal with like multiple depots, heterogeneous fleets, when we have to assign a root or some customer to an attribute resource. And finally, we have maybe the most study of the three, the root evaluation attributes, which are the ones that deal with the feasibility and cost computation for each root. Still, considering the last type of attributes, which are maybe the most essential ones, since they are the ones that are required even to treat like the simpler variants like the CWRP over preview time windows. A very generic framework has been proposed, widely used in the literature, which is the one of the resource extension function. This framework, while being quite generic in the representation it achieves, it also is quite able to be implemented in a very efficient way. And in the end, it boils down to finding a resource that represents our constraint for a given sequence or an entire root, and then define a concatenation function, which is our resource extension function, which is able, given two resources of adjacent sequences, to obtain, make the concatenation, obtain the resource of the resulting sequence, in a way that by induction we can compute the state, the resource of any root in an efficient way. On the other side, if we consider all the techniques that has been proposed during the year, we are in a very similar setting in a way that also in this case we have a huge variety of Meta-Heuristics, and the hybridation of this one when is not really clear, maybe the classification. From my point of view, well, what I'm trying to do is taking also, in this case, from the literature, when we can see that pretty much every new paper that tries to propose a new technique also do the work of schematizing it into different components. So as a framework, what I'm really trying to do is, in a way, isolate all these recurring components. We can find different techniques, generalize them, and put them together, like available to be then composed, like starting bottom up, starting with single components and play like Lego and putting them together to build algorithms. To make this thing clear, I will try to make an example of the process, a very simplified process I've gone through, like trying to generalize local search operator. Local search operator are a very specific component of local search's algorithm. It pretty much is describe a kind of a transformation we want to do to a solution to obtain a neighbor solution. And what we might think as a first implementation is to just write a simple function that first check if the move is improving, if it's feasible, and then it apply. However, this kind of approach has a series of problems. First of all, if we want to make really generic this kind of approach, we can't really just assume that these three are the steps that we want to do every time we consider this operator. We don't know that maybe we want to apply a non-improving technique, maybe because we are trying to move from a local optima, or maybe we want to move on the feasible solution space, so we can't assume feasibility. And also, we can't assume that we want to apply every move that passes the previous checks. Like maybe we are considering a list of candidate moves without applying them, and only apply one of these moves, like the best one, for example. So as a design approach, what really I tried to do in the framework was to, okay, let's try to apply a very narrow separation concern, minimize the scope of the operator and make it only deals with the geometric side of a move. So it will only encode the move in some way, and also it only deals with geometric feasibility. Geometric feasibility is a way that with which I describe like it will not create subtours inside our solution. Then for all the other components, we will use like a customization point, like I don't know, callback if you're programming C, or in this case, a lambda function are also an efficient way to implement this in C++, where we will be able to express our move acceptance, which can be anything, can be a feasibility, it can be improvement, or also can be something like simulated annealing move acceptance, can be anything that we want, and also what to do when we actually have a move that we want to apply. In this way, we have kind of abstracted away every detail that is not really essential for a local search operator, and then we can use this local search operator in any way, in any combination that we want. However, it's easy to describe how to do, but all of these kind of assume that there is still a way to communicate between different components of the algorithm. Because, yeah, we don't compute feasibility, for example, inside the operator, but we still need a way to compute it somewhere. And this is done by finding a way to represent, a generic way to represent a move that will also kind of introduce the least amount of overhead possible. I skip all the kind of iteration and trials I made during the past month to kind of produce a representation that was expressive enough, but also keeps the overhead kind of minimum, and describe directly what I'm currently using. So suppose we have a very specific operator, just to consider the case where we have a lot of static information, compile time information, that we can kind of exploit during our implementation. In this case, we would like to be able to encode all this static information in a way that it will not create overhead at runtime. Using a segment-based, concatenation-based representation of our moves, we can see that, first of all, for the neighborhood we usually explore in vehicle routing is quite a natural representation, since we usually move sequences of customer from a route to another or within the same route. So it's quite a natural way. So it's a good way. It simplifies reasoning about it, but also we can also notice that it kind of divided the move into 6 different parts, and this simplifies how we encode this static data. Like, we know that there are 2 moving segments and 4 that remain unaltered. We know a lot of stuff of these segments, like the one that are moved, one of size 2, the other of size 3. We know the direction. No one of the 2 are flipped. Of the 4 other segments, we also know that we only need a node to represent them, because the other side will be the depot. So we know kind of a lot of information. So what we really need to know at runtime are only the 8 node IDs that represent these segments. And if you think about it, these 8 node IDs are also the 8 nodes that were part of the 8 edges that we will remove from the original solution, and will part of the 4 new edges that will be introduced. So it is a kind of a minimal representation. And from some tests that I did, the compiler is often able to understand this kind of representation with pretty much everything in code at compile time, and transform this representation into a very equivalent version that doesn't use a representation, but just work with directly with the solution. So how we did like in C, where maybe or not in C, like how we did in a very specific algorithm where we know how the solution is made, and we kind of modified it on the fly. So if we can to extract general rules of thumbs, when we kind of consider components for a framework, first of all, we really have to work to make the scope of our components as small as possible. and then achieve expressivity with composing this component. Also, narrow scope components will help with the separation of concern, which will be helpful for scaling up a framework, simplify the reasoning because we know each component what will do, what is his objective, and also kind of enable a partial specialization of this component that we will start maybe with some very generic and general implementation that will then specialize a little bit, and we will be able to do it because it's already kind of isolated from all the rest. Then the other thing that we really want to do is avoid assumption as possible. Like if we don't really have to take an assumption, it's better to leave it like on the side and maybe accept like customization point in a way that the outer algorithm that we'll use, for example, the local search operator will customize it. So all this talking is generic talking. Well, what I also wanted to do is to show how it is to work with a very composable framework. So I try to create a little demo that just show how easy it could be just to take some different components and exchange them and see what changed in the solution. Maybe it will be quite a trivial test, but what we will do is take an algorithm, a very simple algorithm in this case, like a ruin recreate with a simulated annealing acceptance criteria inspired to Caesar. We will choose an instance to simplify also the testing, and we will just try to change how we manage distances, which is one of the simplest things to change, but also is one of that mess more with how our algorithm perform. So as a starting point, well, first of all, we can start using double as a representation because it's quite a flexible kind of type. And also, there is this abstraction within the framework where we are not really using function pointer to represent our function, but generic classes. So in this way, we have function with state. It can be a direct call to a function pointer if you are considering a tsplib distance function, or could be like we could see into a cost metric. So we could, for example, also make a query to Google Maps. So anything, it just can have a state. So we can run our algorithm, and these are our initial timings that are not really meaningful, are just a starting point. In my laptop, it lasted for 70 seconds, while in the workstation, it took 50. The first thing that we might consider is if using floating point is really worth it. Since they are very versatile, they have a wide range, and also they provide many decimals that can be useful if we are not sure if we will have to deal with integer or exact distances. However, usually when we deal with the doubles, we have problem with tolerances and precision level that I assume will be the same thing in this case. So every time we make a comparison between double, like if something is improving or something is equal to another value, we also have to consider that double values always have some kind of noise, and maybe to almost identical solution only varies on like the 10th decimal digit. Also, if we consider to have tolerance, we are kind of wasting a lot of bits because all the representation that double can, all the number that double can represent that use more decimal than one that we are interested in are kind of wasted because we will never use it. We are like, okay, if we only want 2 decimal, but double let us use like 10 decimal, all those representations are kind of wasted. And the same thing also apply for precision. If we have a precision like we want an integer precision, we can't really use all the values of a double because after 2 to the 53, we will notice that 2 adjacent representation of doubles, so we have a distance of 2 units. So if we add 1, we kind of do not modify the value. So we also kind of waste representation on the higher side. A possible solution, temporary solution that we'll lose a little bit of generality is to try with integer distances, and we leave everything as identical and just run again the experiment, and we will see that we kind of get a 10% to 20% improvement with respect to using double. And this can be also kind of surprising for some of us, because with modern hardware, it is also quite often told that nowadays doubles, floating point, and the integers are like treated in quite the same speed. However, like the IEEE standard still dictate that some compiler optimization that we can do with integers are not like applicable with floating point, like out of order execution or something like that. So we still have some optimization that can deal with, can optimize better our algorithm that may be available, but we cannot use them with doubles. So trying with integers could be also helpful to try to understand if there is this kind of, our algorithm can kind of exploit this optimization. So we lose generality using integers, but one of the easiest solutions that we can also find in the literature is to simply scale our integers. Like if we want three decimal point, we can just multiply by 1,000 and we have our 3 decimal point. However, from a framework point of view, it's kind of not a very clean way to just enforce a scaling everything everywhere in the framework. So you have to deal with the scaling pretty much everywhere, or even in parts of the code that doesn't really have to deal with the logic of how you represent distances. So a neat thing that we can do is to introduce a zero-cost abstraction, zero-cost with an asterisk, because there are not really zero-cost abstraction, but almost zero-cost abstraction that just enclose an integer and accept like a level of precision and will make it the scaling automatically. In this way, the only overhead we are adding is every time we compute a distance, we are adding a multiplication for, in this case, 100. So there is only a multiplication along with the distance computation. And indeed, we lose a little bit. We go from 10 to 20 to 7 to 17 improvement on the timing with respect to the initial test. Finally, when we are kind of done with considering many different ways, many different data that we can use to store distances, we might start to think, okay, but why we need to every time call a function pointer is not really efficient. We can try to think other kind of thing. And one very general case is to simply define a threshold. Under this threshold, a threshold size for our instances, and under this threshold, we will compute a cost matrix. In this case, we will compute the distances only once and simply reuse them. In the framework, we keep in mind the composability aspect. We will simply define the old distance provider as a fallback, and then define a new one which is adaptive. It will accept the fallback and the threshold, and if the instance is behind the threshold, it will use a cost matrix, otherwise it will use the fallback. With this simple, very, very basic optimization, we can see that we already have a 27 to 45, almost we are half the time. And we pretty much did nothing. Also, from an implementation point of view, we just fiddle out with a couple of lines of code. So it was quite an easy test to do and just to see what changes. And also, we didn't really give up any kind of generality because we are still able to handle any kind of size, because if we are going over 10,000, we have still the fallback. However, if we consider the usual sizes we are dealing with, this kind of threshold doesn't really make sense, because we pretty much never have to deal with instances whose cost matrix doesn't fit in memory. Like if we consider like 16 gigabytes of memory, even 40,000 customers can still fit in under, I think, 12 gigabytes. So we still have space with modern hardware to compute a cost matrix. So we can pretty much clear all this kind of adaptive aspect and just use a cost matrix always. So at the start of when we read the instance, we compute the cost matrix, and then we have pretty much the ideal case where there is no overhead. Also, the multiplication we had initially with the scaled int, at this point will not be really a problem anymore because the scaled int are just stored, so we don't have to multiply. We already have a scaled instance. And indeed, we obtain a speed up and time improvement still with respect to the initial case of 55 to 56 to 66 percent improvement. So we have more than half the time. Finally, just for completeness, I wanted to add, okay, let's consider if we really cannot compute a cost matrix. Maybe we are like solving the Mona Lisa 100K, like we have a distance of a size that doesn't let us compute a cost matrix, or maybe we don't have RAM. But we are really focused on on finding a good solution for this instance only, so we kind of know which distance it will use. In this case, I decided to use the classic TSP-lib Euclidean distance. And let's see what changes in terms of times when the compiler is not anymore a function pointer, so the compiler has full visibility of the function. It knows that, for example, is a pure function. It will not modify some global state. It will just consider the input and compute an output. And indeed, what we find, and is better represented in this final slide, is that this was kind of surprising to me. It goes almost better than the case where the cost matrix was adaptive. And the third case, the fourth case, the scaled int with an adaptive cost matrix, is kind of a good representation of how caches work with distance function. We know that caches can be a good way to speed up distance computation. But this is true if we don't really know our distance function, because as soon as we consider we have a distance function that is known and is relatively simply, the compiler is capable to do much better. And in this case, it's quite more difficult to find a cache that will be able to even speed up the last case. So this is all here. The references I cited during the presentation. Thank you for your attention.
Well, that's quite fascinating, Francesco. So you're saying that instead of computing a huge distance matrix, in many cases, you are better defining the distance function and letting the compiler do its magic.
So in this case, well, I didn't mention it because it was quite technical, but the framework is pretty much all C++ metaprogramming. So when we pass something with angular brackets, we have pretty much provided it explicitly to the compiler in every point of the framework. In this case, what we have done with this writing, the compiler will know that exact distance is used in every point we call the distance, so it will be able to inline it. It will be able to vectorize it if it can, and do all this kind of stuff. And this really helped. While when we provide a distance pointer to a function, we kind of blocking and losing all the optimization that compiler engineers are working throughout all the years to try to really speed up our code, because function pointer is really oblivious to the compiler. It can be anything. It cannot do assumption. It cannot do if it's a very complex thing. It's a very simple thing. One of the optimization that I try to do is we can use built-in compiler attributes, which are not standard. Every compiler has a way to provide more information. And you kind of can add attribute to some function to tell you, okay, this is a pure function. A pure function is a function whose result only depends on the input. So you know that if you call twice the same function with the same input, it doesn't have to call a second time. And indeed, with this kind of approach, you can kind of obtain some of the speed back. But still, a function pointer is kind of a problem from a compiler optimization point of view.
We could also maybe discuss it later, but I was just wondering, since you do everything in compile time anyway, did you ever do a benchmark where you actually encode the metrics in compile time? So to see whether that actually makes like a big difference, because I would expect the compiler to do some very, very interesting stuff.
So I don't think so. It shouldn't make any difference because at a certain point, what really makes the difference is the memory, how you access memory, with which pattern you access memory. So even if you encode your matrix at compile time, it will still be stored somewhere in memory. Maybe it will not be in the heap, but it will be in another kind of segment of your executable. So it makes not a lot of sense. I could try, I didn't try, so I could not tell you that it's kind of the same. But still, if the matrix is quite big, you will not be able to store it in the cache. And still, every time it will cause a cache miss and have all the same time performance of a normal kind of allocation. This is my conjecture. I don't have a result on this.
Do you have, let's say on your own laptop, do you have an idea of the amount of instructions per cycle? Because I want to get a feel for the memory throughput, just the cycle throughput, and how much of this is memory constrained.
I never measured it, also because it's quite very hardware dependent.
Yeah, but your laptop is the same on all of this.
I didn't heard it.
Your laptop is the same across all of this. It has a particular set.
Yeah.
I just want to know how that changes between these different things.
I didn't measure that. I didn't measure that, so I don't really know. What I'm trying to do is every time I have a completed component, try to make it in the old way, like where you know everything, you implement it without trying to make stuff generic and composable, and see how much it differs, and then try to make the generic stuff converge to the same kind of instance. Because one of the starting point of all this framework is to achieve generality without losing performance for as much as possible. There is always kind of a overhead, like for example in the distance function, on the move representation, which pretty much, if you use a cost matrix, it has pretty much the same exact performance of doing the check using the resource extension function manually. Instead, this is kind of automatic and adapted. But as soon as you use a function pointer, the version that with the solution representation kind of get worse, because the compiler is less capable to reason about this abstraction. Like, I know that in theory it should be able to, and with some playing with the built-in attributes, I'm able to kind of make it reach back the same performance. But out of the box, it is not always able to understand the abstraction you can give it. So this is the kind of reasoning I'm trying to do for the moment. Yeah, it's still ongoing work. So. Okay, thank you very much.